All right, thank you for tuning in today, and we'll just go over a couple of ways to point us in the right direction here and get you on your way. I believe that this was set to be due on Wednesday. I think we'll still stick with that. So upcoming next week, we'll go ahead and you have time to work on this on Tuesday, and then we'll see once where we're at that time. Okay, so one of the things, maybe like number 3, we'll try to point you in the right direction here. And that would be, for instance, says how many grams of magnesium phosphate are produced in the reaction below if you have 754.77 grams of magnesium hydroxide. One of the reasons we'll partially balance that to point you in the right direction, because this one is a little tricky. No one would argue with that. So magnesium hydroxide. Oops, it's in the wrong spot. I should have left it there. See if you would have said, he's doing it wrong. Okay, plus, what is it? Phosphoric acid. Yep. So H3PO4. Okay, gives us our, we'll go ahead and write it HOH as water. And then looks to me like we got some magnesium phosphate. Okay. PO4 times 2. All right. So that's Mg3PO4 times 2. All right. So once we write it like this, it's probably going to help us out a lot because it says we've got 2 hydroxides here and only 1 over there. But keep in mind, where's the best place to start with these reactions is usually with a metal. So we got 3 magnesiums on the right side and only 1 over here. So if we put a 3 on this side, okay, that balances out our magnesiums, and then gives us 6 hydroxides. And that's why starting with that is probably going to help you out in the long run, because now that we've got 6 hydroxides on the left, and remember, you only have 1 over here, so you're probably going to put a 6 in front of that, and that will help you out, like I said, in the long run. So if we have 754.77 grams of this substance, we want to know, okay, how many grams of magnesium phosphate. So we're going from this side all the way over to there. Okay, so again, 4-step problem. We've got 754.77 grams of magnesium hydroxide. Okay, so it's fine to write it like this, just as long as you keep referring back to that. You don't always have to write Mg parentheses with 2. As long as you refer back to that, you'll be just fine. Okay, so there's step 1. Okay. So what we do is, notice we have this in grams, so we want that to cancel out. So we put grams of magnesium hydroxide down there, and that gives us a mole of magnesium hydroxide. Okay, just like what we've been doing for the last week and a half or 2 weeks or so, changing grams to moles. That's nothing new. And then in this 3rd step, it allows us to change what we have, which is this substance, into this over here, or magnesium phosphate. Okay, so for every mole of magnesium hydroxide, we put moles of magnesium hydroxide. I said that wrong, didn't I? If I could just back up just a moment. For moles of magnesium hydroxide, we would get moles of magnesium phosphate. That's what I meant to say. Notice we've got a mole to mole ratio. Okay, so right away we already know that we see a 3 here, so we need to put a 3 on the bottom. Okay, and then I don't believe there's a coefficient that goes in front of there, so we're in moles of magnesium phosphate is where we need to be. So for every mole of magnesium phosphate, we put grams of magnesium phosphate up top. Okay, so you're going to have to fill in the amount of grams of that magnesium hydroxide there and that magnesium phosphate here. And just remember to balance out the rest of your chemical reaction, and then you'll be able to fill this in just fine. If you remember from, I want to say, of course, 2 years ago when you were a freshman and you took this class, when it came to balancing these chemical reactions, we did an exercise in the lab where with this stoichiometry, we went ahead and made predictions on how much of this is going to be made. Now, we did that as a class. One of the aspects that you'll do, whether with a partner or on your own, is do this same type of process, but we'll have you make a prediction on what type of yield you're receiving. And that's what the main function of stoichiometry is, or what it does, is converting one substance to another. And maybe what a chemist would do is just try to decipher, is there a better way of making things? And with that, you would do that on pencil and paper to figure that out. So that's problem number 3 that would hopefully try to point you into the right direction. And then as we look on the back page, I know there's another tricky reaction on there. I think it has to deal with making of steel. Okay, that's problem number 7. And the reason that is so tricky is because you have oxygen in 2 separate spots on the reactant side. So as we look at that, it says iron is generally produced, iron is generally produced from iron ore in the earth through the following reaction in the blast furnace. You have 4,000 grams of iron ore are available to react. How many moles or carbon monoxide are needed? Okay, so what it's saying is, in this case, the reason we say how many moles are needed is our next step in this stoichiometry process is limiting reactants. Okay, so this would be an example on how we would solve some of them. And what that means is, if we have iron 2 oxide, okay, and we're reacting that with carbon monoxide, okay, how many grams of carbon dioxide are given off, then it gives us our pure iron then as well. Okay, and again, what's so tricky with this is we see iron in 2 separate spots, or not iron, we see oxygen in 2 separate spots. Okay, so what you would do, typically you would say start with your metals, and I would agree that's what you'd want to do. You have 2 on the left and only 1 on the right. That's pretty simple. Go ahead and do that. So now our irons are balanced, but now we've got 1 to 1 with the carbons, and we've got 4 to 2 with that of the oxygens. And what you might think is, okay, so if we got 4 and 2, we put a 2 here. Now your oxygens are balanced, but now we got 2 carbons, okay, and only 1 over here. And the moment that you do that, now your oxygens aren't balanced. You got your everything but your oxygens. 2 irons, 2 irons. We've got 2 carbons, 2 carbons. We've got 5 oxygens to 4 over there. So what you would do, okay, is in this trial and error, and some of you might have this done already. Okay, what I'm going to actually do is point you in the right direction and say partially balance this and put a 3 there. Okay, then once you've done that, then the math should fall into place. So in this case, we've got 4,000 grams of iron ore. Okay, so how many moles of this are actually needed? Because when we do these limiting reactant problems, let's say, for instance, you need 350 moles of this to get that pure iron sample. But if you don't have 350 moles, you only have 300, well then your yield of iron might not be as great, and that's why knowing what the limiting reactant is and what you actually need would help you out in the long run. And that's why we go through that problem solving of limiting reactants. So now you got this set up, again, just partially. Now we got the hard part done. We'll go ahead and let you finish that problem. Okay. So then maybe one more. I see we're up to about 10 minutes. I didn't want to take a lot of time here. Just something to help point you in the right direction. And let's see here. Okay, maybe number 2. How many moles of oxygen are required to react with 18.12 grams of aluminum in a synthesis reaction? Okay, so we've got aluminum plus oxygen. Remember, that's diatomic, and that's going to give us Al2O3. All right, so now, since those are odd, these come in pairs, we're going to get this up to an even number. We got 6. Got 3, and now we've got 4. Okay, now we've got that balanced. So we have 18.12 grams of this. We want to convert it to, was it moles? Aluminum oxide. Okay, so it's just a 3-step problem. So again, we got 18.12 grams of aluminum. Again, we'll let you fill in the blanks. There's step 1. So grams of aluminum down here, that gives us a mole of aluminum. Next step is our mole ratio, because it's asking for moles of this substance. So for every mole of aluminum, that gives you moles of aluminum oxide. That's what we're looking for. So we have to revert back to your balanced chemical reaction. We got 4 on the bottom and 2 up on top, and that's how we would actually go ahead and finish that problem. All right, so I see we're up to, again, getting close to 12 minutes. I didn't want to take a whole lot of time, so hopefully that helps you out and points you in the right direction. Enjoy the rest of your weekend, and we will catch up to you next time.